Look around you. From the phone in your pocket to the car in your driveway, our modern world runs on portable power. We take for granted the ability to carry electricity with us, to untether our lives from the wall socket. But this freedom is the result of a long, fascinating and sometimes mysterious journey. A journey that began not a century ago but potentially over 2 millennia. What if I told you that the fundamental concept of a battery might have been discovered more than 2,000 years ago? Our story begins not in a modern lab, but in the sands of ancient Mesopotamia, near modern-day Baghdad. In 1938, archaeologists unearthed a peculiar object dating back to around 250 BCE. A simple clay jar containing a copper cylinder, which in turn encased an iron rod. Known as the Baghdad battery, its purpose remains one of archaeology's most tantalizing puzzles. When filled with an acidic liquid like vinegar or grape juice, substances readily available at the time, this simple device could have generated a small but noticeable electric voltage. But for what purpose? Theories abound. Some scholars propose it was used for electroplating, a process known as gilding, to coat silver objects with a thin layer of gold. Others suggest a more mystical application, perhaps used by priests in religious rituals to create a tingling sensation, seemingly divine intervention to all followers. Or maybe it was an early form of medical analgesia. While scientists still debate its true function, the Baghdad battery stands as a remarkable testament to ancient ingenuity, a possible flicker of electrical discovery long before its time. After this mysterious prelude, the science of electricity lay dormant for centuries. The real journey to the battery we know today began with the spark of the scientific revolution. Thinkers began to systematically investigate the strange force known as electricity, initially through the study of static. The crucial breakthrough came from a famous scientific disagreement in the late 18th century. Italian physician Luigi Galvani observed that a dead frog's legs would twitch when touched by 2 different metals. He believed he had discovered animal electricity, an intrinsic life force. But his contemporary Alessandro Volta was skeptical. He hypothesized that the electricity came not from the animal, but from the contact between the 2 dissimilar metals themselves, with the frog's bodily fluids acting merely as a conductor. He famously proved his point by placing 2 different metal coins on his tongue, creating a circuit that produced a distinct tingling sensation. No frog required. This debate spurred Volta to create a device that would prove his theory beyond all doubt. In the year 1800, he unveiled his invention. It was a simple yet revolutionary column, a stack of alternating zinc and copper discs, separated by pieces of cardboard soaked in salt water. He called it the voltaic pile. Unlike the fleeting sparks of static generators, the voltaic pile was the first device in history capable of producing a stable, continuous electric current. It was the world's first true battery. With this single invention, Alessandro Volta didn't just win an argument. He unlocked the door to the electrical age, setting in motion a chain of innovation that would forever change the world. At the turn of the 19th century, electricity was a mysterious force, seen only in fleeting sparks. The prevailing theory, from Luigi Galvani, was animal electricity, a vital fluid inherent to life. But another Italian, Alessandro Volta, was skeptical. He suspected the electricity in Galvani's famous frog leg experiment came not from the animal, but from the contact between different metals. Volta embarked on meticulous experiments. He discovered that when 2 different metals, like zinc and copper, were connected by a moist conductor, a consistent electrical potential was created. To amplify this, he created a revolutionary device, a stack of alternating zinc and copper discs separated by brine-soaked cardboard. He called it the voltaic pile, the world's first true battery. For the first time, humanity had a source of continuous electric current. Unlike the instantaneous discharge of a Leyden jar, the voltaic pile produced a steady flow of energy. In March 1800, Volta announced his invention to the Royal Society of London. The news was met with both excitement and skepticism, as it challenged the deeply entrenched theory of animal electricity. Volta gave dramatic demonstrations across Europe, inviting scholars to experience the continuous shock from his pile. The device was so influential it even captivated Napoleon Bonaparte, who was fascinated by its potential. The voltaic pile wasn't just a new gadget, it was a paradigm-shifting tool that unlocked an entirely new field of science: electrochemistry. Within weeks of Volta's announcement, British scientists William Nicholson and Anthony Carlisle used a voltaic pile to split water into hydrogen and oxygen. This process, electrolysis, was a revelation. It proved that electricity could drive chemical reactions, inspiring researchers to explore this newfound power. The most brilliant pioneer of this new era was a young chemist named Humphrey Davy. At London's Royal Institution, Davy constructed a colossal battery with over 2,000 pairs of plates. With this unprecedented power, he began passing currents through molten compounds to isolate reactive elements that had never been seen in their pure form. In 1807, he isolated potassium and sodium, and soon after discovered magnesium, calcium, and barium. Volta's invention had become the key to unlocking the building blocks of matter. However, the original voltaic pile had a critical flaw. The chemical reaction produced hydrogen bubbles on the copper plates, an effect called polarization, which caused the voltage to drop off quickly. A more stable battery was needed. The solution arrived in 1836 with the Daniell cell, invented by British chemist John Frederick Daniell. His ingenious design used two different electrolyte solutions separated by a porous barrier. This prevented hydrogen buildup, resulting in a far more constant and reliable voltage. The Daniell cell was the first truly practical battery. It quickly became the power source for the burgeoning telegraph industry, sending messages across continents. This marked the battery's transition from a laboratory instrument to a commercial utility, setting the stage for the next great leap in electrical storage and the dawn of a truly electric age. While the Daniell cell had proven the concept of reliable continuous current, its liquid components made it fragile and stationary. The world needed a more robust solution. That breakthrough arrived in 1866 from French engineer Georges Leclanche. His invention, the Leclanche cell, was a game-changer. It consisted of a zinc rod anode submerged in an ammonium chloride solution with a porous pot containing a carbon rod cathode packed with powdered manganese dioxide. This design was less prone to spillage and required far less maintenance than its predecessors. Though still a wet cell, its practicality was undeniable. It quickly became the standard for the rapidly expanding telegraph networks, railway signaling systems, and electric bells, proving that reliable electrical power could be packaged and deployed where needed. But the liquid electrolyte remained a fundamental limitation. The quest was on to create a battery that was truly portable, one that wouldn't leak or dry out regardless of its orientation. Chemists and inventors across Europe and America began experimenting with ways to immobilize the liquid electrolyte without sacrificing its conductive properties. The pivotal moment came in 1886, when German scientist Karl Gassner developed what is widely considered the first commercially successful dry cell. His genius was in creating a paste-like electrolyte by mixing ammonium chloride with plaster of Paris to create a jelly. He also used a zinc casing for the battery itself, which doubled as the anode. This innovation was revolutionary. Gassner's cell was spill-proof, compact, and could operate in any position. He patented his invention, paving the way for mass production of truly portable power sources. The impact was immediate and profound. In the United States, the National Carbon Company began mass-producing the Columbia, the first dry cell battery marketed to the general public in 1896. This coincided with another brilliant invention it enabled, the portable electric light or flashlight, introduced by Conrad Hubert's American Electrical Novelty and Manufacturing Company, which would later become Eveready. Suddenly, personal portable light was a reality. Beyond flashlights, these new dry cells powered doorbells, ignited the engines of early automobiles, and brought early telephones to life, fundamentally changing daily life and creating the very first market for consumer electronics. The transition from cumbersome wet cells to convenient dry cells democratized electrical power. Small workshops evolved into large-scale factories to meet the surging demand. Companies like Eveready in the US and Varta in Germany were established during this period, becoming industrial giants that would shape the 20th century. The underlying chemistry of this new technology, known as the zinc-carbon cell, was elegant in its efficiency. The outer zinc casing slowly corrodes, releasing electrons in an oxidation reaction. These electrons travel through the external circuit, powering a device, to the central carbon rod. At the carbon cathode, the electrons are consumed in a reduction reaction involving the manganese dioxide and the electrolyte paste. Over the decades, this chemistry was continuously refined, improving the battery's shelf life and its ability to handle the higher power demands of new devices. By the turn of the 20th century, the disposable dry cell was a fixture of modern life. The fundamental design, a metal anode, a cathode, and a paste electrolyte sealed in a compact container, created a blueprint that would dominate the primary battery market for 100 years. This era of innovation not only put power into the hands of the people, but also set the scientific stage for the next great leap: the quest for a battery that could be used again and again.